research is a thing where you should expect to fail. So sometimes people forget about that. They want to have success only. We're on the verge of Exascale. There's a machine at Oak Ridge National Lab that's about to be lit up, the Frontier system. And the other thing that we're looking at are methods that I refer to as responsibly reckless.
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hi, Shaheen. Great to be with you again. We're really pleased to announce that today's special guest is Jack Dongarra. Jack's title is Distinguished Professor of Computer Science in the Electrical Engineering and Computer Science Department at the University of Tennessee, among other fellowships and honors. Jack's arguably one of the world's leading computer scientists, something confirmed recently when he was named the winner of the ACM's Turing Award, sometimes called the Nobel Prize of Computing. Jack, welcome.
Oh, thanks very much, and thanks for those kind words. It's a tremendous honor to be this year's recipient of the ACM Turing Award. When I think about well-known names from past awardees, I'm really humbled to think about how I learned from their books, read their papers, used their programming languages, their theorems, techniques, their standards, their algorithms, their numerical methods. And I even wrote a couple of papers with a few of them. So I'm really incredibly proud that the work that we have done, the software packages, the standards, the performance tools, I was part of creating. But there was even a more important role that was played by the community itself, which had a hand in all of that, and whose members felt that the work was important and really needed to be carried out. So an award like this couldn't have happened without the support and contribution of many people over time. And I have to give credit to the generations of colleagues, postdocs, students, staff members at my institution who helped and really, I'll say, influenced me over the years to obtain this recognition. So it only came about by having a great group of people and mentors who push things in the right direction. I hope I can live up to the distinction that the other Turing Award recipients have provided, and I want to become a role model, as many of those Turing Award recipients have been, for the next generation of computer scientists.
That's wonderful.
And I guess when I look at things, I'm now one of 4 numerical people who have done numerical work who have received the award. The previous ones were Richard Hamming, Jim Wilkinson, and Velvel Kahan. So I really feel quite honored to be included with their names.
That's beautiful. Jack, I think the whole community is so proud, so well-deserved. And thank you for having the perspective that you always had, and so accessible and so just wonderful in all manners.
Why don't we start off with a kind of a general question? Shaheen and I were wondering about your thoughts in general on the future of supercomputing as HPC converges increasingly with AI and enterprise computing.
Right. So machine learning and AI are really important tools that computational scientists will use, as well as be used in many other areas. We see it having just a tremendous impact in terms of things like voice to text to speech, document analysis, fraud detection, image and video analysis. So AI is fueling, in some sense, a revolution on how, I'll say, business and researchers think about problems and how we can formulate computational solutions to them. So the machine learning and AI will help computational scientists be able to come up with approximations to solutions much, much faster than, I'll say, traditional methods have. And from those approximations, we could perhaps use conventional models or conventional methods to refine the solution and come up with something which is much more accurate. So I see, great promise for AI on the horizon. These large-scale computational models and AI-driven analysis are really now pervasive in many aspects of business, e-commerce, science, and engineering. And they have important implications as a result. If we take a look at, I think it's the Science 2021 Breakthrough of the Year, it was for AI-enabled protein structure prediction. So there's a good example of using AI to really have one of the major breakthroughs in 2021 with transformative implications in biology and biomedicine. So I think we're just discovering how machine learning and AI are going to benefit us and how we're going to be using them as a tool to help us move forward. And as a result of that, we see a lot of activities, a lot of companies trying to leverage that. We see a lot of hardware startups exploring new ideas that are driven by this AI frenzy. We have companies like Cerebras and Sambanova and GraphCore are just examples of those companies that are building hardware which can help us get even a stronger foothold in terms of how this is going to shape out in the future.
Jack, when you look to the future, the other trend that's coming is quantum computing. And just when it looks like we're finally getting our arms around GPUs, and maybe FPGAs, maybe not, quantum computing is coming. What is your perspective on that?
Well, quantum computing is, again, going to be a tool that we use. The way I view quantum is we're not going to replace our conventional computing system with a quantum computer. What we're going to do is to augment our conventional computing system with quantum computational components. And by that, I mean, I see a future HPC system having a spectrum of things. And that spectrum has, conventional CPUs in the form of a multi-core kind of processing. It'll have GPUs that we currently have on our systems. That's the way we build high performance machines today with CPU, GPU combinations. In the future, I see that expanding to have FPGAs and machine learning hardware and perhaps neuromorphic components, and quantum computing will be a component on that spectrum, as well as optical computing and maybe some kind of neural engine. So quantum computing is going to play a part. It's going to be used when the computation can benefit from that type of computation or that mechanism for carrying out the quote computation. And it's not going to replace our computing. We're not going to be solving PDEs with quantum computing. I don't see that in the future. But quantum has an edge on certain kinds of problems and domains, and it'll be used for those domains, I hope.
And speaking of future trends, I was just working on a story about changes at OLCF and Exascale Computing Project, and the news was announced that Ashley Barker will handle procurement for Exascale successor systems, which HP has talked a little bit about publicly, but they're looking at systems that are obviously increasingly powerful, but also increasingly adept at handling multiple workloads at once, having to do with, traditional HPC simulations, but also advanced machine learning and data analytics. The term that they use is the Internet of Workflows. So as you were saying, Jack, this convergence of AI, HPC, and multiple architectures and capabilities all working together.
Right. I think workflow is the right mechanism to use in this case. And we see more and more applications fitting into that model of workflow. So we put together a continuous stream of components that are persistent and that can be used for that particular application to carry out their computation. And that workflow has in it various hardware components which assist in developing that. Some of those components would be in place on site. Other components would be perhaps acquired through a cloud-like environment, so they can be put together on demand to get to the place that they need to in terms of the computational resources that could be drawn on to help with that workflow environment. So I see that as a reasonable approach to things.
It almost sounds a little bit composability.
Yeah, composability, exactly. And that's one of the strengths, I think, of the cloud. It allows a user to compose something, not having to have a persistent piece of hardware on the floor. They can compose it, use it for a period of time, and then move on and do something else, and then perhaps recompose something which is similar, but may even have more computational ability because of the cloud itself acquiring additional hardware to solve that. Today we buy a machine, we put it in place, we use it for about 5 years, and then we have to replace it. It's a big investment. It takes a lot of effort to stand up that piece of equipment, and moving to a cloud-like environment may make sense as we go forward. We're on the verge of Exascale. There's a machine at Oak Ridge National Lab that's about to be lit up, the Frontier system. It'll probably come in about 2 exaflop in terms of its theoretical peak performance. And, it's got about 8 million cores in it. And that's a staggering amount of computational power. And, it's made up of conventional CPUs plus GPUs. And if you really want to get at that 2 exaflop number, you've got to use the GPUs. The GPUs provide 98% of the performance for that machine. If you think about a conventional program and you want to run it on that machine, you really got to think twice about running a conventional program, which is just using the CPUs or maybe has some communication so you could put together processes. You really got to exploit those GPUs in the computation in order to effectively utilize that very powerful piece of equipment that they're about to stand up. So, the world is changing in that way. That's the programming model that we have to address. How things shape up in the future will probably be different, but that's what we have today.
Jack, while we're talking about the future, just to cover the possibility, it's been mentioned for a long time, this whole idea of a biological computing. I think I first read about it many, many years ago, and it kind of shows up and then it disappears. Just about a couple of years ago, people were talking about storing a lot of data in a piece of DNA or something, like milliliter of fluid would include all the encyclopedia or whatever. Is there anything new in that realm? I mean, we talk about quantum computing that conjures up these other ways of doing computing. Is that happening?
So I think there's a lot of exploration going on today, and some of that is in the realm of, I'll use the words science fiction kind of things. But I think there is something there that needs to be explored. That's the beauty of research. We let ourselves think about how we can exploit these things, and then we go off and conduct experiments to see, in fact, if we're capable of achieving what we thought we could with those things. Quantum computing certainly falls into that category, and looking at biological computation, looking at neuromorphic computing, trying to understand how we could effectively use that kind of thing, given the limitations that they might have. You mentioned they can store lots of stuff, and I believe that's true. The concern could be, what's the response time? So you're able to store a lot of things, but then what about the retrieval? And can that really be used effectively in driving a computation when we have exascale or zetascale capabilities behind it? How can we drive that kind of computation given the mechanisms that perhaps can be put in place? So I think there's a lot of issues there. I think it's good that we experiment. Perhaps we're doing too little of that kind of experimentation today. With research, research is a thing where you should expect to fail. So sometimes people forget about that. They want to have success only. I tell stories about my students who come in. I give my students a problem to look at and ask them to think about solving it. And inevitably, they'll come back within a week or two and say they have no idea how to solve this. And I say, that's perfect. That's exactly what should happen. That's a research problem. You shouldn't know how to solve it. If it wasn't, I wouldn't give you something that you could solve immediately. So go back and think about it. And then they go off, and ultimately they'll come back and be successful and come up with some kind of solution for it. So, we should expect to fail. We should expect to try things. It's part of the game. So you're not going to be a winner all the time. Nobody expects that to happen. And we learn from those mistakes that we make along the line.
Oh, I think protecting basic research is one of those eternal vigilance things, because it truly is the fountain of everything else that comes.
Yeah, exactly.
Now, speaking of Exascale, Jack, the news broke last week about China and the Sunway Taiyu light system. And these university researchers there have announced kind of a breakthrough in many-body quantum simulations. And I was curious about your response to that news. If you view where China is with their supercomputing, can we assume that they've reached exascale? And is this sort of a threat to us, or do you look at it more as a spur for our own R&D?
It's a great thing. So I'm encouraged by what I see in China and also in Japan. So in China and Japan, they've gone off and done their own thing. In the U.S., the machines that we're standing up under the Department of Energy's Exascale computing program, so we're putting in place 3 computers in the US that are going to be able to achieve exascale computing. And those 3 computers from 10,000 feet look exactly the same. They have CPUs and GPUs attached to make them work. And we're using commodity processors. So we're using multi-core processors from AMD and AMD GPUs in one case. And in the other case, we're using commodity processors from Intel plus Intel's GPU. So the commodity is the word that's being used there. And we do that because we can leverage those components. We try to get better cost effectiveness out of that. And in China, and also in Japan, but mainly in China, they were embargoed from those parts. So the US government imposed embargoes. And the result of that has really spurred research in China to develop their own hardware. So you mentioned the new Tahoe light machine, the Ocean Light, I think is it, or Sunway Pro Ocean Light in Guangdong. And it's a machine which has over an exaflop of computing capability. There's a rumor that they've run the Linpack benchmark on the machine and achieved over an exaflop. It's a powerful machine. It doesn't use Western processors. It uses a processor that was designed in China. There's some question about where it was fabricated. It may have been fabricated in Taiwan. I don't know the answer to that, but people in China might say Taiwan is really part of China, so it was a Chinese part. And they've run the benchmark, the LINPACK benchmark on the machine. That's the rumor, but they haven't submitted it. So there's a question as to why they haven't submitted it. And I don't have a good answer for that, but I'm hoping that when the US announces their Exascale machine, the Frontier machine, and I expect that to be up and running and announced for the June release of the Top 500, which is coming up. Maybe China will announce their machines as well. So yes, China has done a very good job of developing the architecture for the Tahu series of machines. The Ocean Light machine, I think, is the one you were referring to with that mini-body quantum simulation. That was part of last year's supercomputing Gordon Bell Prize, which they were successful with. So they won the Gordon Bell Prize for that model. And we see another machine in China, that's the Tianhe 3. We don't hear too much about it, but it's a machine that's based on an ARM technology with their own accelerator attached to it. And again, around exaflop kind of performance is what they're reporting, or what the rumors are anyway. And even in Japan with the Fugaku Light, so there's an example of a machine which is built using an ARM processor along with a vector component which was designed by the Japanese. Again, not using what I'll say commodity processors, not off-the-shelf kind of things, but exploiting architectural differences to extract performance. So that's a very well-balanced architecture that the Japanese have put in place. Very impressive in terms of what they've done with that architecture. So Japan and China have made what I would call major advances. The U.S. is also in position to deploy their Exascale machine. So if there's a race, we're neck and neck, I'll say. When you take a look at the top 500, there's a number of things that come out of that. In terms of the number of machines on the top 500, China has the most machines of the top 500 list. U.S. is second, and Japan is third. So, there's something there about competition. There's also something there about China understands that these machines are important. They're important for the industry that China has. They're important for science, and they're devoting significant resources to making sure that they have the equipment that's necessary to do those kind of computations. Today science is driven by simulation. Those simulations are carried out on our supercomputers, and people understand that the one with the fastest, best supercomputer may be able to do the best science as a result.
Jack, one criticism that is leveled at the Chinese systems, albeit without detailed knowledge of their architecture, is that they are not as efficient. They don't have as much memory bandwidth. The ratio of performance to memory bandwidth limits the set of applications for which they really could perform. And that's a stark contrast with Fugaku, which sort of looks like it's at the other end of the spectrum and does a really fabulous job of being as general purpose as these things can get. And with the US systems, probably closer to Fugaku. That obviously in the context of competitiveness, it can be a bit of a solace to say, okay, we're not that far behind. Okay, they did do that, but it's really not quite. To what extent do we need to take that in the context of a race? Are they ahead, or are there still things they have to really go solve before they catch up?
Well, yeah, those are good questions. I don't really want to see it as a race. And too much attention, I think, is given to these benchmarks that we have,
right?
Which is the other thing that's underlying all of this. So, the LINPACK benchmark, okay, if we take a look at it, Fugaku is number one. If we take a look at the performance, Fugaku, we have the U.S. machines. Summit is the first machine from the U.S. that's listed at number 2. And China has number 4, the existing Sunway Tahu Light that was reported a few years ago. And those machines all achieve what I'll call pretty good performance on the LINPACK benchmark. So we see numbers on the order of 75 to 80% of the theoretical peak for those machines. And that brings up, I think, a problem with the benchmark from a number of angles. That benchmark, the thing we call the LINPACK benchmark, was designed in the late 70s. And if we think about what was happening with computers in the late 70s, the machines that we had were quite different than the machines we have today, in the sense that floating point arithmetic was very slow on the machines of the 70s and compared to data movement. So floating point was very expensive. Data movement was not really an issue. And the benchmark that we had, the LINPACK benchmark, was a good approximator for many scientific computations where floating point was the important thing. Today, that benchmark doesn't really reflect the kinds of applications that people are running on the big machines. If you take a look at what DOE is running, they're trying to do simulations of large-scale three-dimensional partial differential equations. In looking at those 3D problems, there has to be a discretization that takes place, and that discretization leads to a system of linear equations, but the matrix is quite different than the LINPACK matrix. The LINPACK matrix is characterized as a dense matrix computation. The kinds of things that people are using machines for today, 3D partial differential equations, the matrices that come out of that are sparse, and we need a different kind of method to solve those. So the method that we have is an iterative method. It's a method which works on that sparse data structure and constructs a number of iterations to approximate the solution, and that approximation is carried out until we get some kind of convergence. Where I mentioned that today's machines for LINPACK get about 75 to 80% of the theoretical peak, on this other benchmark that we have, the HPCG benchmark, a high-performance conjugate gradients benchmark. Conjugate gradients is a method that uses a sparse matrix technique to solve that underlying system of equations, very similar to the way in which problems are solved on our large machines today. What we see for that problem on the big machines, Fugaku, from the Summit, from the Chinese machines, we end up with something on the order of 3% of theoretical peak.
Right.
So we get something with going from 75% to 3% and even less. 3% is what Fugaku gets. So that's that's a well-balanced architecture. Summit, for instance, gets about 1.5% of the theoretical peak. And again, it's related to data movement more than anything else, also related to the fact that we employ GPUs to get additional computational power. And, the GPU, you have to pass data to that GPU, carry out a computation, and then force to pass data back to the front end, to the CPU part of the machine. Our dirty secret, perhaps, is that many of the machines that are in use, many of the supercomputers, the ones at the top of the list, get a very small fraction of their potential when solving real problems. And the benchmarking has to be done correctly to really understand the capability of these computers.
Can I ask, are you looking toward a day where the top 500 will be ranked by a different benchmark?
So I would say the top 500 serves a purpose. And part of its purpose is to look at trends in the area of high-performance computing. And I think it does a pretty good job of that. So I wouldn't want to abandon that data. I wouldn't want to throw all that data away. What I would like to do is to come up with another set of metrics that can be used to evaluate our machines. And we really need a whole spectrum of measurements here to capture what these machines are capable of. So we have this benchmark I just mentioned called the HPCG benchmark, which tries to capture something about solving three-dimensional partial differential equations. But we also do other things with our machines, and we should try to look at benchmarks that might do a good job of reflecting what that important application looks like on these machines, and then try to evaluate things in a way which maybe even combines different benchmarks and tries to understand what the mix is. So I'm not an advocate of replacing the top 500. I'm more an advocate of augmenting it with other benchmarks. We have another benchmark which looks at this area of using mixed precision. So we think about doing a computation using 64-bit floating point arithmetic. That's the way in which we've done things in the past. But mainly because of machine learning and AI coming onto the scene and the realization that those problems don't require full 64-bit arithmetic, we can get away with shorter precision. So we see hardware today which does 32-bit, 16-bit, and I know NVIDIA just announced their newest GPU, Hopper, which can actually do 8-bit floating point arithmetic. So I'm not advocating using 8-bit floating point arithmetic for our simulations of PDEs, but there may be a way to effectively leverage some of that lower precision computations in our standard mix of simulations that we do in order to extract performance. Because when you go down in terms of precision, you usually get a factor of 2, maybe more, of performance out of it, and less data movement, which helps the overall picture of performance. So I'd say that we need to look closely at exploiting this newer hardware that's on the scene and trying to use it in our numerical simulations. And many people are looking at this. So what I'm saying is not a new thing. There have been many reports of using 32, 16-bit arithmetic to carrying out parts of the computation. And some interesting methods and approaches have been proposed that can exploit that kind of hardware. And one that I'm familiar with is trying to exploit that 16-bit, the lower precision, as much as you can, and then using some mathematical techniques to recover the full precision, the full 64-bit accuracy, and doing it at a much lower cost than you would have had you done the original computation just with 64-bit arithmetic. So I think there's a lot of things that could be pursued here on a research level, and I think people are starting to look at it very closely.
Jack, I remember when HPCG, the conjugate gradient benchmark, was being discussed, and before it got launched, there was also a discussion or proposal perhaps that maybe FFT could be part of this mix. Can you explain the thought process that led you to say it's better be CG rather than FFTs?
I think FFTs play an important part in our simulations, and we should look at providing a way to measure and to understand what the capabilities are. My own background is in linear algebra, so I'm drawn to linear algebra. Mm-hmm. But having said that, we have an effort at Tennessee, which is being done with support from the Department of Energy's Exascale computing program, to look at benchmarking FFT solvers. So we have an active program that's looking at that, at what it means, how we can do it, how we should rank these machines. We have different software packages which complicate the story, and which of those software packages should be used, and how can we evaluate the software and the hardware in this mix. So it is an ongoing process. FFTs are an important thing and should play a part in this way in which we measure things, but it's just one of the components that should be used in a measurement so that we can better evaluate the overall hardware and software ecosystem that's in place to help us in solving problems.
Yeah, definitely. It really is a decathlon rather than a single event, isn't it?
Yes, it is. I think of it always as a marathon you're about to run with the software and hardware and these things, and it's not a sprint. Right. So it's got to be something which takes, a lot of effort. It's going to take time.
Excellent.
Jack, in the world of algorithms, are there novel ones under development that you think might have the potential impact of something like linear algebra?
Oh, yeah. There's a lot of things that are being explored. So the research is very vibrant, I would say, for the linear algebra field. Linear algebra impacts so many areas that, there is always interest in it. So today, there's a lot of interest in things called randomization methods. So randomization methods are methods so usually with linear algebra, we have a matrix, an array of data that comes from some experiment, and we want to produce some solution to it. We want to solve systems of linear equations, AX equal B, or maybe an eigenvalue problem, where we want to find the eigenvalues and eigenvectors of a given matrix in order to effectively drive some computation. And these randomization methods do a sampling of that matrix to try to extract its features, if you will. So it produces a reduced set of data, and that reduced set of data is refined and provides an approximate solution to the problem. So, then the question is how good is that approximate solution? And, there's many ways to adjust things and to get things. So randomization ideas in linear algebra are an important area. It's a relatively new area. There's a lot of research going on. Some very interesting methods are being explored, and I see it as a very vibrant thing. The other thing that other algorithms that people are looking at are algorithms that minimize data movement. So again, the computers that we have are over-provisioned for floating point arithmetic. That is, they have a tremendous amount of capability for doing floating point, but where they fall down is moving data from one part of the machine to the other. This is the memory wall that people talk about. So data movement's extremely expensive. Floating point is cheap, and that leads to a situation where the conventional wisdom is when I look at an algorithm, I want to count the number of operations. And if I have a lower count for my algorithm than your algorithm, my algorithm is better. But that conventional wisdom gets thrown out. And it gets thrown out because of data movement. Data movement is an important part of looking at the performance of an algorithm. And if we just look at operations, we're going to be misled because the hardware that we have is over-provisioned for doing floating point. And the more expensive thing is the data movement. So algorithms that do more operations may actually take less time to get the solution. So that conventional wisdom, I think, needs to be adjusted in light of what we have. And the other thing that we're looking at are methods that I refer to as responsibly reckless. I always like to come up with a solution which is accurate. So if somebody gives me the input data, I want to do a computation and give them back an answer, which is a correct answer, which is done in a way that I can say something very positive about. And most of the methods we have are that way. But there are some methods which, if we're given a problem, may produce an answer which is not precise or not as good as the algorithm by the traditional method. The idea with responsibly reckless algorithms is you try an algorithm which runs extremely fast, but may produce an inaccurate solution, but it's able to tell you that it's inaccurate. So we have ways to check to see if we've gotten the right answer. And if we don't get the right answer, we abandon that and maybe go back to a conventional algorithm where we know we're going to get a better answer. But if we're correct, if we're able to use that fast algorithm, we're able to get something much faster. So that's the responsibly reckless part of this process. So we have a number of algorithms which fit into this category where they're very fast at getting the solution, and they have a mechanism for checking to see if you've got the right answer. And if you got the right answer, you're done and you move on with that very fast solution. If you get the wrong answer for some reason, because the algorithm is flawed, then you abandon it and resort to that more traditional algorithm and take more time. So for a few problems, you may take more time, but for many of the problems, you can come to a solution which is adequate and gets there much faster. That's another approach that we're looking at.
That is excellent. Jack, is the future all PDEs and graphs that we try to linearize? I always have to ask this question.
Well, that's the standard method. That's the way in which we think about it. So we have a three-dimensional problem, which is nonlinear, and we take that and we try to linearize it and come up with a solution for a small time step, which may be accurate. There's many issues with that, and there's a whole branch of mathematics which looks at quantifying the uncertainty that we have in our methods. And we need to look at that and try to understand better if those approaches are going to produce answers which are reasonable. And that's an important area of work as well. So again, there's a branch that should be followed, and people should look at it because it's important.
You've mentioned data movement twice. Is there a technology in existence or that's kind of coming online that you think could be particularly effective in addressing that issue?
I only wish there was. Moving data through the memory hierarchy is an expensive process. We spend tens of thousands of cycles moving data from primary memory in through various levels of cache up to the point where it's in registers and can be done. And then maybe you have to move it over to GPUs to actually do the computation. And then, once we get it there, it's blindingly fast. Just to put that in context, my laptop is a good example. My laptop uses an Intel processor, and it has the ability to do 3264 floating point operations per cycle. That's an incredible amount of computing power. 32 floating point operations adds and multiplies. It can process per cycle. And that's on a one core. And now we've got multi-core. And now, the problem is, how do I get the data to that part of the machine where the computation can take place? That's the struggle. And that's always been the struggle. That memory wall is there, and I don't know of anything that's going to help us get over that. Maybe optical computing, where we can move data around at the speed of light. That may overcome some of those issues.
What do you think of processor in memory, or try to move compute to data rather than data to compute?
Yeah, that's a good idea. And we're seeing that kind of architecture start to appear. In some sense, GPUs provide some of that capability.
Right.
The issues are that the memory is not as vast as they are on the CPU part of the machine. But, even on GPUs, the memory is starting to expand. So that's certainly something that helps. Stacking memory is a way to accommodate that speed issue, putting that close to the processor, having it really soldered onto the chip itself, using chiplets in some fancy way to do this. Those are all ideas and concepts in the hardware components of the machine that perhaps can aid in making things run a lot faster. So there are mechanisms there to explore and to identify. One of the problems, I'll say, is that we're stuck in some sense of relying on commodity off-the-shelf parts. There was a time, I remember, when we had a vast array of architectures that were proposed that could be experimented with. I'm remembering this time when we had computers, we had companies, even startups, that were investing in machines that could adequately allow us to explore this space of things. We had machines that were, I'll just throw out some names, guys like Thinking Machines,
Yes,
Convex, and guys like Terra, and companies that were producing machines. Intel Paragon is another example where we had this whole collection of experimental machines that were available to us to experiment with, and Denelcor and various companies that produce machines. They were unsuccessful. The market is tough on these companies, but they were ideas, architectural ideas that got embedded in hardware and let us experiment with it. And many of those ideas we see emerge on some of the machines that we have in place today, and the techniques are important as we go forward.
Jack, as you may know, for the past 10 years or so, the Sunday before SC, we have a Dead Architecture Society meeting.
Is that right? I didn't know that.
And it's a time to remember all of these guys. You're absolutely right. There were like tens of them for a period. Yes.
Yeah, I mean, Ardent and Kendall Square and
Alliant and
Encore and
Wavefront and N-Cube and
N-Cube, AM, that's right, DAF, and
that's right, the Transputer. It's
RIP, right?
Yeah, RIP indeed.
Jack, just in our remaining time, I don't know if you'd like to indulge in some futuristic thinking, but looking maybe out over the next 10, 15 years, where do you think big advances in HPC might come from? What will that look like?
Okay, so I did allude to some of that earlier on. So one of the things I discussed earlier was the fact that we're going to have the spectrum of devices that could be drawn on to help us in our computational quest. CPUs and GPUs certainly fit there, but there could be FPGAs and specialized hardware that might do machine learning, neuromorphic quantum, having optical computing perhaps play a role. There's a spectrum of devices there that could be put together in a computing system and letting the user draw on those components that make sense for various parts of their computation. So the computing ecosystem is today in a state of flux, creating both challenges and opportunities for high-performance computing. The way we have to think about these computational systems, HPC systems, is like a very sophisticated, large-scale scientific instrument. There's a lot of similarities between devices that we have, like the Large Hadron Collider or the Square Kilometer Array, which is a device put in place made up of computing devices, which is going to be used to carry out that very specific scientific purpose. We talked about workflows. There's a tremendous workflow with each of those, the LHC and the SKA and LIGO. And getting that workflow right and having the right components that can help with that is going to be an important aspect to it. So science with respect to high-performance computing may be driven by those kind of specialized architectures which are designed and built for that specific area that it's going to be targeted at. And components will be updated and replaced over time, but the overall framework, that workflow idea, is going to be the thing that's persistent with it. There's a cloud computing aspect to this as well. We're at Exascale today. Will we go to Zetascale? Is that something that's going to be attractive or tractable even? Or should we rely on cloud-based systems to provide the computing capability that can be composed and then abandoned? I'll use the word abandoned, but
released.
Released, that's right. That's a better word to use. And have that available for somebody else. The question really is, how many times does one need the whole machine, that whole exascale machine, to do a computation? I believe there are times when it will be used for that purpose. But for most of the time, it'll be used to run multiple jobs simultaneously on the machine. And, we might be better off in that case to use cloud-based computing. So I think there's many things there to be explored and looked at. The incentive for cloud-based computing, we have companies that invest tremendous resources. They're even building their own hardware. This is amazing to me. Amazon's building their own hardware. We've got Google building their own hardware to meet the needs of their cloud-based computing. That's incredible in some sense. They're not relying on Intel or AMD to provide the parts. They're going off and designing their own parts. It shows that they have a tremendous amount of resources at their disposal. The words that Dan Reed and Dennis Gannon and I use is they're exothermic in terms of their resources. They have tremendous capability, and they're going to use that capability to deploy the right hardware. If you take a look at the government and its acquisition of machines, it's not exothermic in terms of its resources. It's endothermic. It needs things to carry out its work. There's a big difference there in terms of how you can push the technology. And we see cloud companies maybe investing a lot in that cloud technology.
That's brilliant.
Great. All right. Well, we'll have to end this, unfortunately, sadly. But Jack, just great to have you, and I hope you'll return to chat with us again.
Very good. It's been a pleasure. Thanks so much.
Thank you very much. Excellent.
Thank you.
That's it for this episode of the At HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The @HPC podcast is a production of Orion X in association with Inside HPC. Thank you for listening.